So plus 0.9642. So this is giving us minus 5.852. So when we subtract this from 9, we have the voltage drop across the parallel arrangement. Okay. So this is giving us 3.2148 volts. Okay, so it means that this is the voltage drop across the resistors in parallel. If we have the voltage drop, and when resistors are connected in parallel, their potential difference or voltage drop across them are the same. So this is B would be 3.2148. A would also be 3.2148. If we have found the PD across them, then because they also have the same resistance, 2 ohm, 2 ohm, they will have the same current flowing through all of them. So when I calculate the current flowing through A is the same as the current flowing through B, because resistances are the same, potential difference are also the same. So VIA is equal to 3.2148 over 2. Okay. So 1.6074 ampere would be the current through A, which is also equal to current flowing through B. In terms of potential difference, we could have also done this. We could have also done this. You see, we determined the equivalent resistance of these two in parallel and got 1 ohm. So that parallel arrangement is also equal to 1 ohm. R equivalent 1 ohm. So once we have the PD across C, PD across the internal resistance, we subtract, and that would be what will be left will be the PD across the parallel. Or since current of 3.214 flows through all of them and then comes here, we could have determined the voltage drop by current 3.214 times the resistance, which is 1 ohm, and it would have given us the same value, 2144 volts, just as we summed the two up and then subtracted to get. So there are a lot of ways to go around this. Please, is the solution okay? Hello.
Yes, dear.
Hello, Deborah.
Mr. Dear, please, what are you finding?
The
Mr.
question.
Dan, please, can we go over the solution again?
Okay, let me please pay attention. Let me go over for the last time. Deborah, pay attention. What am I finding? I'm finding you. We have this circuit. We have resistor A, whose value 2 ohm. resistance B, another same value B. This is resistance C. Okay, what's the value of this 1.5? The question says that calculate for the current in each resistor. So therefore, that's what we are finding. We are calculating for the current in each resistor. Are you okay?
Yes, please.
In doing so, please do not forget the fact that we've been given an internal resistance of the cell. If there is no internal resistance, fine. But the moment it is given, you need to work with it. Okay, so Beryl, Edith, Erebia, Gerard, Irene, Nana Jemfoa, Rachel. This girl was here, Anadwa. So if the internal resistance is not given, that's fine. But please, the moment it is given, you need to treat this as if it is another resistor. You must treat this as if it's this. It's like this. (0.30) in series. You must treat this as this. If it's not given, fair enough. When it's given, treat it as if it's in series with this. So in actual fact, it is like having 4 resistors within a circuit, 2 in parallel, 3 and 4, because it is given. Now we are calculating for the current in each resistor. Okay. First, what I must do is that I must determine, to get current, to calculate for current, we will need potential difference across them, because we will use Ohm's law, and from Ohm's law, V is equal to IR. Therefore, I will be equal to V over R. So to find the current, we need a voltage drop across this one's in parallel, this one, and this one. Okay, we can only do that if we are able to find the current flowing through the circuit, the source current. So the source current I can be calculated if we have the total resistance within the circuit, because we know the total EMF. So RT is equal to this parallel resistance 2 times 2 over 2 plus 2 plus, in series with it, 1.5 plus the internal resistance 0.3. This will give us the total resistance within the circuit. Please, are you okay up to this point? Are you okay up to this point?
Yes, please.
This is 1. So 1 plus 1.5, 2.5 plus 0.3, 2.8 ohm is the total resistance. Therefore, the current I from the source current I is equal to 9 volts divided by total resistance of 2.8 ohm, giving us 3.214. Rachel, is that the answer?
Yes, please.
So once we have the current, it means that the current starts from the positive. When it gets here, breaks into two. When it gets here, it will rejoin. Don't forget, this one will come here, then this one will also come here. By the time it comes here, it is the same I. So it means the source current will flow through the 1.5. The source current would also flow through the internal resistance. So straight away, we can find the current IC flowing through the resistor C. And that will be equal to 3.214. The current that will flow through the internal resistance R, IR, would also be the same value. We are left with the current that will flow through A and B. Once I know the current flowing through this, I can determine the voltage drop across this and this, because the source voltage 1, 2, 3 are in series. So the voltage drop across this plus this must be equal to this. So if I know this, I can subtract the sum of this and this from this to get this. Okay, so let's find the voltage drop across C. So VC is equal to its current, which is 3.214 times 1.5. And this would give us what is the value of the voltage drop across C?
4.821 voltage.
Okay.
Oh, sorry.
Then V, the lost volt, would also be 3.214 times 0.3. And that is 0.9.
0.964 volt.
9642
volt.
642.
Yes.
So when we total VD across this and this, we can find the voltage drop across the parallel arrangement to be 9 minus 4.821 plus 0.9642. Just sum and subtract it for me.
3.2148 volts.
148.
No, 2148.
Oh, okay. 3.214 volts. And so this is the voltage drop across this parallel arrangement. And when resistors are connected in parallel, they have the same voltage drop, meaning the voltage drop across A is this. The voltage drop across B is this. If we have C, D, blah, blah, blah. So long as they are all connected in parallel, they have the same voltage drop. The other good news is that the resistors have the same resistance, 2 ohm, 2 ohm. So current, which is equal to V over R, because they have the same V, they have the same resistance, then the same current would also flow through them. So this would be equal to I I of A will be equal to I of B, which is 3.214 over resistance of 2. And this is equal to this is equal to
1.607.
1.607 ampere. So Deborah,
Mr.
this is what we were calculating for.
Yes, please.
Please, is it understood by all? Irene, are you okay?
Yes, please.
Gerard, Nana Jemfua, Nana Mary, are you okay?
Yes, sir.
Are you fine with the
Yes.
solution? All right. So let us continue with the lost voltage and then look at when resistors are source of EMFs are also connected in series and all that and parallel. In addition to the lost volt concept. So in our last meeting, we realized that if you have a source of EMF and then you connect a voltmeter across it, this is E. You have the voltage drop across the voltage drop across or the voltage reading to be equal to the EMF of the battery. So if maybe the battery EMF is 1.5, the voltmeter also reads 1.5, and this is determining the terminal voltage at no load. Determining the terminal voltage at no load when no resistor is connected in the circuit, or when there is no current flowing through the circuit, because the voltmeter has a very high internal resistance and it will prevent current from passing through it. Now, when you connect an external resistor within a circuit, if you connect an external resistor R, and then you connect a voltmeter across the resistor, you realize that EMF is not equal to the terminal voltage across the voltmeter. The voltmeter reads a value which is less than the EMF. So it is as if some voltage is lost. So this situation is as if there is a lost voltage. And we realize that the lost voltage is as a result of the internal resistance of the battery, R. So the lost volts is due to the internal resistance of the cell. It also drops some voltage. So to account for that loss, we realize that the source EMF E must be equal to the terminal voltage across the resistor V plus the lost volts. When we are able to account for the lost volts and we add it to the voltage drop across the resistor, which this is measuring, we'll get that equality. So E is equal to terminal voltage plus the lost volt. So the lost volt small v is equal to the EMF of the battery minus the terminal voltage, which is the voltage drop across the external resistor. So where small v is equal to the lost volts by the internal resistor, and V is equal to the terminal voltage the voltage drop across the resistor, across the external resistor. Of course, E is the EMF of the battery. All right. Now, the lost volt, the internal resistance of the battery, is also similar to what we've just done. It is also as if it's in series with the external resistor. Please, this is a voltmeter, which is actually not part of the circuit. But because we want to measure the potential difference across the reason for which we connect it. So the internal resistance of the battery small r is as if it is in series with this big one. Please, are you with me? Hello. So if this is in series with this, then the voltage drop across this plus the voltage drop across this must be equal to E. If the source current is I, then the same current will pass through this, and the same current will also pass through this. So the expression for the terminal voltage, big V, is equal to I times R. Then the lost volt, small v, because the same current will also pass through, is equal to I times small r. So when we put that into the equation, we have big E equal to I from here, IR plus I small r. Therefore, when we factorize big I out, we have R plus small r. Okay. So sometimes this is what the equation to use to find whether you are to find internal resistance, the external resistance, and all that. I'll look for questions because I'm out of Cape Coast. I don't have my question bank, but I'll be going by Monday. I'll bring questions on this so we can apply to solving the problem. So this is the whole concept of EMF of a cell, the terminal voltage, and then the lost volts. Please, any question?
JW, don't clean it now.
I'm not cleaning. We are going to look at when the battery, the EMF, a number of batteries, each with internal resistance. How do we find the current? So from here, we can also find the current I flowing through the circuit to be equal to E over big R plus small r. This is the expression for the current flowing through the circuit. I is equal to the EMF of the battery all over the external resistance R plus the internal resistance R. Now I'm going to modify this. We have maybe 2-3 batteries, each with internal resistance R. This is connected to an external resistor R. One is an external resistor. So if this is not there, if there is no external resistor, then we connect a voltmeter across this. Then we are to get the voltage drop across this be equal to the source EMF. So if each of the battery has 1.5, 1.5, 1.5, then we expect the voltage drop across the battery to be equal to 4.5 volts. And this is something we always can confirm in the lab. If you connect 2 batteries and then you connect a voltmeter across them, the voltmeter must read something close to 3 volts. Please, are you with me? Human beings or beings?
Yes,
Are you with
please.
me? So if 3, the voltmeter must record something close to 4.5, and you'll be seeing this in the lab. But the moment you connect an external resistor within the circuit R, and then you connect a voltmeter across it, the reading on the voltmeter is less than the EMF of the battery. If this is 4.5, you see this recording a value less than 4.5, around 3 and all that. And this is because of the internal resistance of the battery. Okay. This is due to the internal resistance. So if I'm asked to calculate for the current flowing through the circuit, I know the EMF, source EMF total, must be equal to the voltage drop across the resistor V plus the lost volts by the internal resistance. Since each of the resistors appears to be in series, so in actual fact, if we are drawing a circuit, this is how each of them will look like. 1, 2, 3. Each with an internal resistance R, R, R. And so when currents from the source gets to this point, the current, the external resistor is in series with this, and this. Okay, each of it will drop the same volts. All right, and so the voltage drop across this will certainly be I times big R plus the load volts. Because I have three, this will be I times 3R. These are in series, and when resistors are in series, the total resistance RT would be equal to R1 plus R1 plus another R1. They are the same. They have the same value. The reason for which I have 3R. Please, are we okay? Are we fine?
Yes, please.
All right, so we have I R plus 3I R. When we factorize I out, we have R plus 3R. Now, the EMF2, you see, when you have batteries in series, connected in series, the total EMF is always an addition of the individual EMFs. So, because we have 3 batteries, then the total EMF will also be 3E. 2 or more batteries connected in series. So 1.5 volts in series with another 1.5. Okay, the voltmeter will measure that number of times the single EMF. So 3E. Therefore, the current I, in this case, the current I will be equal to 3E over R plus 3R. In effect, what I'm saying is that if you have any number of cells, connected in series, if there are n number of cells connected in series, each with an internal resistance R, the current flowing through the circuit is always equal to, look at this one, when we have 3 cells, total EMF became 3E, the total internal resistance also becomes 3R. So when you have n number of cells, the total EMF becomes NE over R plus n number of internal resistance. So for n number of cells, the current through the circuit would be equal to this. And this is when the cells have equal or the same internal resistance. So that's number times R. Please, are we okay? Are we okay here?
Yes, please.
Because we'll look at it for parallel arrangements too.
Mr. Dia.
Hello, Mr. Deborah.
The job is I can't see the top there one to write.
Now you can see.
Yes. Thank you.
So for n number of cells connected in series, okay, the total EMF is n times the individual EMF of the batteries. And if each of the cells has an internal resistance R and they are equal, then the current through the circuit is equal to n number of EMFs all divided by R plus n number of. Now, sometimes we can disturb you a little bit. The disturbance is that I can set a question, create a very beautiful question. 3 barrels. Barrel. Is she gone? So I have 3 batteries, each with internal resistance R. Now, the external resistance will not be a single resistor, but I can craft the question in such a way that R1, R2, R3. This is a similar possible circuit that can be given to you. It's the same thing. Calculate the current I flowing through the circuit. And here it is the same I is equal to n number of cells, because the cells are connected in series, divided by R plus n number of R. Over here, the whole trick is that the external resistance is not just a single resistor, but it is given in combined circuit so that you find the total resistance for this arrangement. Example. Let's solve an example. Look at the question we just solved. Assuming each of the batteries has EMF 3 volts. Each EMF is equal to 3 volts with internal resistance of 0.3 ohm. If this is 2 ohm, this is 2 ohm, this is 1.5. Find the current flowing through the circuit. That's the question. Find the current. Find the current I. Flowing through the circuit. Make me proud. Each of the EMFs batteries has an EMF of 3 volts with internal resistance of 0.3. This is 2 ohm, 2 ohm, 1.5 ohm. Find the current I flowing through the circuit. So make me proud.
Mr. Udia,
Hello.
is that the diagram for the question?
Yeah, this is the diagram.
Okay.
So each of the battery has an EMF 3 volts and an internal resistance 0.3. The batteries are connected in series.
Sir,
Yeah, there are.
so I think the current is 2.647.
Okay. So take note of your value whilst we wait for them to also come up with their answers. All right. Is somebody true apart from Gerald? Hello. Nana Joa, Nana Jimfua, Edith, Burial, Nana Ya. Is somebody else true?
Lydia.
Nah,
Lydia.
Mary.
Yes, I had 2.09 ampere.
2.09 ampere. And Gerard, what did you also get?
Please, I had 2.647.
Okay, so we have
Mr. Dia,
Mr. Deborah.
Mr. Dia, please add 2.647
Okay, so let's see.
ampere.
So it's from here, I would be equal to n number of EMFs. So 3. Okay, 3 times 3 all on. So I must represent this as if it is 1. Okay, so our total is equal to, we found this is 1 plus 1.5. So 2.5. So R is 2.5 plus 3 number of 0.3. So we have 9 over 2.5 plus 0.9. So 9 divided by, sum this up, this is 3.4. Divide 9 by 3.4. What's the answer? Divide 9 by 3.4.
Please, the answer is 2.6471 amperes.
2.647.
Ampere.
Okay. So that's it. Okay. So this has been given in that cumbersome way. But the idea is just represent this as a single one whose that is equivalent to this number. So I can even expand this, baby. All that I expect you to do is represent this as if it's a single resistor. Please, all is well.
Yes, please.
Okay. Another banger. Another banger. I can also arrange the resistors, the batteries in parallel or parallel. Is it parallel or parallel? Then connect it to, this has an internal resistance R. This also has an internal resistance R. Connect this to a source of an external resistor and ask you to find the current I flowing through the circuit. The point is also that if there is no external resistor and you connect a voltmeter, the voltmeter will record the EMF. But the funny thing is that for resistors connected in parallel, if one of the EMFs is 1.5, this other one 1.5, we wouldn't have the voltmeter will not record 3 volts. No. But it will record only 1.5 volts. This goes to buttress the point that oh my earpiece is disturbing. Hello, can you allow me to charge in about 20 minutes time so you rejoin, because it will be going off anytime soon. Hello.
Yes,
I beg
please.
you, because we haven't finished at all. That I want us to do a lot. So please, let's go in about 20 minutes time for me to recharge this. Okay.
Yes, please.
Okay. I beg you, come. Nana ya bury and go. Ide tell now, Mary and okay, bye-bye. Rachel, bye-bye. 20 minutes time, you rejoin.
Bye.